Hi everyone, and welcome to another video from Eric's Electronics Workbench. In this video, we'll be going through this Boonton Radio Company Model 230A signal generator power amplifier. We'll take a look at what adjustments or repairs might be needed to put it back in service. So let's get started. Alright, on the bench today we have this signal generator power amplifier made by the Boonton Radio Company. It's type 230A or model 230A. Now, if you're not familiar with the Boonton Radio Company, they were formed in 1934, and then in 1959, Hewlett-Packard purchased the Boonton Radio Company. So you'll often see products that were manufactured by Boonton Radio continue on as Hewlett-Packard products, and this would be one such example. This is the Model 230A that was originally manufactured by Boonton Radio, but then did continue as a Hewlett-Packard product. Now, I have the service and operating manual for this unit, and you can see on the front it says Hewlett-Packard 230A, so they did continue that product on. The Boonton Radio Company catalog from 1963 to 64 has this model listed in it. So I'll go ahead and put those pages up on the video now, and you can pause the video if you'd like to see the specifications and what they had to say about this particular model in that catalog. It's interesting to note that price of $1,200 in 1963, that was a lot of money. So this was not an inexpensive product, as all HP gear over the years was produced to the highest quality standards. This was no exception. So let's take a look at the front panel, and then I'll turn it around and we can take a look at the back panel as well before we open it up and see exactly what we're dealing with inside. I really don't know what the condition is, so we'll be finding this out as we go along. Now, on the front panel, there's the RF level volts. So this is the voltmeter for the output, and the RF output and the RF input over on the other side. Of course, power switch, a band switch for the different bands. This is 10 megahertz to 500 megahertz, so a very usable range. And the purpose of this, as I mentioned, it's a signal generator power amplifier. It's made to be connected to a signal generator, and it boosts that signal generator's output up to about 4 watts maximum. So it gives you a little more output power to, if you needed to use that on a device for testing. It just gives more output because most signal generators don't go to that level of an RF output. A lot of times signal generators will go to very small, microvolts of output or even less, but they don't often go up, with a lot of power. So this is where an amplifier like this comes into play, and you can use it to boost the power as needed. So again, it has a 10 megahertz to 500 megahertz range, and it's selected by this band switch. And then the tuning is accomplished over here through that dial, and there's a vernier control for this, for fine tuning. Now you can see the input and output just the way I received it. It has these adapters on here. If we take that adapter off, the input and output is the same. So this is just a BNC to TNC connector, or adapter I should say. And the TNC adapter is actually an abbreviation for threaded Neil Consolman. That was named after the inventors of this type of connector. And this connector is basically the threaded version of a BNC connector, which is a very popular and common type of connector, but this is the threaded version. So it basically has the same diameters. It looks almost the same, it just doesn't have that bayonet type connection. It's threaded instead. So also on the front panel, of course, we have the power switch, indicator lamp or pilot lamp, and the range switch, and the range is the various ranges that the RF level indicates, and the off position is given if you need to disconnect this meter from the circuit if it's causing an interference problem. That's something that's mentioned in the manual, so you can just electrically turn it off. So looking at the condition overall, it looks really good, of course, for its age. There's no major dings, dents, or anything like that. The top has some scuffs on it, you know, years of things being stacked on top of it, I'm sure. But nothing too serious. Some minor sort of a corrosion, I wouldn't even really say rust, maybe tarnish or something like that, oxidation a little bit on the heads of these screws around here. That's something that could be cleaned up, and we can, you know, deal with that a little bit later. That's more of a cosmetic issue. The front handles on here have sort of a, like a, maybe call it corrosion or like a, it's not really pitting, it's almost little bumps on them. And even the toggle switch has that, and it makes me think this may have been in sort of a damp environment. Maybe it was stored in a damp environment, and that's something we'll need to look at in the components inside. Older resistors can absorb a lot of moisture, so if this was in a damp location, that could be trouble, and certainly means some of those components need to be changed out. So we'll look at that as we go through it. Tag on the front here from the Ryan Aeronautical Company, so a previous owner at some point. Looks like they were using this in probably one of their facilities or labs. So I'll get the unit turned around and we can take a look at the back panel. Okay, here's the back view of the instrument. And you can see over here, here's a data tag that has the manufacturer's name and a serial number, and it actually says Boonton Radio Company, division of Hewlett-Packard Company. There's, of course, the fuse and where the line cord plugs into, and a filter for the forced air cooling. It does have a fan inside. This is a vacuum tube unit throughout. All the circuitry is, you know, based on vacuum tube circuits, so it'll be generating a good amount of heat, I'm sure. Now these sort of oval style receptacles for the line cord, you come across those on some of the older HP equipment, and I do have a cord for that, and you can see that old style sort of oval shaped 3-socket plug, you know, that goes in for the cord. Older style, you don't see that on modern equipment, but it was pretty common on some of these older devices. Okay, the next thing I'll do is take the cover off of the unit, and we'll take a look around inside and see what the condition looks like. Okay, I have the top cover removed. It was just a matter of several screws around the perimeter, and then the cover slipped right off. I also removed this mesh screen that was on the fan on the back. The fan is inside this tube right here. The motor and everything is inside of here, and I wanted to make sure that the fan rotates smoothly, and it does. I want to be able to watch that when it's powered up as well, and make sure that it's running correctly. There's some dust and not really lint, but just sort of a dust or film in there that's kind of built up that needs to be cleaned out as well. So the whole unit inside on the chassis has the typical antique dust you can see in here, just kind of typical. We'll clean that out with some compressed air. But it's looking really good inside from the top view anyways. We'll inspect the bottom in just a little bit. It looks like there's another panel that comes off on the bottom of the chassis. But on the top, everything looks like it's in good condition. Nothing looks overheated or damaged or anything like that. You can see if I tip this up here, the various vacuum tubes down in here. Now, under this cover is the main amplifier section. There's 3 tubes in here for the amplifier. Something I noticed is that this tuning control back here is very stiff. It doesn't turn easily at all. And you can almost hear when I rotate this knob, very stiff, very, very stiff, kind of almost a grinding sound. So that needs to be addressed, and see why that's binding up. Probably some old grease or something has gotten dried up in here. If I tip this all the way up here, you can see this mechanism in here for the tuning. This shaft rotates. These cams, as they rotate, they cause this mechanism to press inward. It pivots across here, and you can see there's a spring right here. In fact, this spring, you know, it has like a old dried grease. It's almost sticky. Sort of a viscous, but kind of a sticky feel to it. I'm sure that's down in numerous areas on the pivots and things like that. These bearings back here. So those need to be cleaned up, and that'll probably free right up again. What this mechanism is doing, it's moving these capacitors in here, and you can see there's, looks like 6 of them, and I don't think there's any up here. Yeah, it just looks like 6. And these are the pistons on the capacitor that push in or pull out as these cams turn right here. So it's part of the RF tuning mechanism. So I'll take this top cover off right here, and we'll take a look at those power tubes that are part of the amplifier. All right, let me tip this up here and we can see inside of there. So the forced air comes through the fan, through this tube, into the housing right here, and then goes through the housing and can come out the vents down here, and looks like a vent over here. There's 3 tubes you can see right here. Down in the bottom there's another tube, and then right here. And those are the 3 tubes that are for the power amplifier. And actually, if I turn the band switch, you can see there. So those coils are being switched into the circuit for tuning across the usable range that the amplifier has. So looking down into the amplifier housing, I can see a repair that has been done, sort of a makeshift repair. It looks like the clamp either broke or has gone missing because they've replaced the original clamp with this very stiff wire right here. And there's 2 wraps around this part that holds the tube into place, and then it's been twisted and it's acting like a clamp. Now it seems to be doing the job okay. The tube is being held in there very firmly. So we'll leave that alone for now. I don't have a replacement clamp, so if that tube doesn't need to be changed or moved, you know, it seems to be doing the job and holding in place, but it should have a clamp like this on the back part of that tube where it's clamping the tube, you know, into the holder. So hopefully that tube doesn't need to come out. If it does, either a new clamp could be made or one would have to be found, but it looks like it's holding for now. All right, I have the amplifier positioned on its side so that I can remove this bottom panel off of the chassis. You can see there are a number of screws that just need to be removed, so I'll do that now. Heads of these screws have become kind of oxidized, you can see on there. So when we reassemble the amplifier, we change those out. We maybe use like a stainless steel screw, something that won't tarnish or oxidize. And that'll definitely clean up this front panel. It looks like with that last screw out, I think we're almost in here. Yep, there we go. More of our antique dust on the panel, but we'll use the air compressor and clean that out. All right, so with the bottom panel removed, we can see it looks pretty clean under here. I don't see any modifications at first glance looking through here, but I do see some pretty old capacitors, and really these need to be changed out at this point. Here's an old wax capacitor, some of these old electrolytics in here. This is probably the main filter cap that's in there. That's this one here. All of those are really going to be aged and probably electrically leaky at this point. So those will need some attention. All right, I have the camera zoomed in a little closer to the electronics below the vacuum tubes so that you have a better view. And you can see things look really clean and original. So good to see at this point. I don't see any components that are overheated or damaged. Wiring looks all original, so all good things to see. Now again, these capacitors will need to be changed out. You know, good all wax capacitor, that paper and foil, electrically leaky at this point, so not even worth testing. These electrolytics won't be very good either. Another capacitor here needs to be changed out, so we'll get that taken care of. Now these ceramic disc capacitors are generally reliable. Shouldn't have any issues with those. The resistors in here are the squared off ends. These are the Allen Bradley style resistors, generally reliable. They don't often drift in value, so we'll test a few and see if they're looking okay. The round end or roundy style resistors were more prone to drifting when they would have the moisture that they would absorb. These are a carbon composition resistor or carbon comp resistors, again like that old roundy style, but these tend to be more stable. You can see that's the type that they've used throughout in here, it looks like. Okay, the next thing to do is reposition the amplifier so that we can try and power it up. And I'll be using that current limited isolation transformer and variac to bring up the voltage slowly. So I'll be back as soon as I get this repositioned and connected. Before we continue on with powering up the amplifier, let's take a look at the vacuum tubes that were used and a quick overview of the schematic. So looking down on the vacuum tubes right here, we have a 6AS7, a 5U4GB. Here's a 6AU6, a 0A2. Over here we have a 3TF4, a 12AU7, and down here in the corner, a little bit hard to see, but right down in here, there's an EA52, also known as a 6923. And then again, in the amplifier sections, the three tubes in here, we have 2C39As or 2C39Bs. So now let's take a look at the schematic. Okay, taking a look at the schematic, starting in the lower left corner right here, we can see the AC line coming in through the fuse and the power switch. And over here we have the voltage selector switch, the blower motor, and then the main power transformer. On the secondary of the transformer, we can see numerous windings. These windings are being used to power the filament circuits. Up here we have a center tapped winding that goes into the 5U4 full wave rectifier. The output of the rectifier is 470 volts DC, and that's applied to the 6AS7. It's being used as a series pass element, and the 6AS7 is a dual triode. The two triode sections are connected in parallel for greater power handling. So the 6AS7's output is a regulated 320 volts DC. We can see there's a voltage adjustment, so we'll want to check that adjustment and make sure that that voltage is correct. So the 6AS7 is being controlled by the 6AU6, and that in turn is being controlled by the voltage reference, the 0A2. You can think of this 0A2 as the tube version of a Zener diode. So that 0A2 is a glow discharge tube or a cold cathode tube. There is no filament in the tube. It just simply glows the gas that's inside of it, and it has a very specific voltage drop across that tube. So that B plus voltage comes out and it goes up to the three amplifier stages up here. It also comes down over here to the meter circuit. Now down here we have a 3TF4, which is a ballast tube. And the 3TF4 is regulating the voltage that's applied to the EA52 rectifier tube, and we'll come to that tube in a moment. So the way that the ballast tube functions is that internally it has only a filament. There's no plate, no grid, no cathode, and it's a very special type of filament. So as more current tries to flow through the tube, it begins to resist more and more. So for example, if the line voltage increases and the secondary voltage increases, without this ballast tube, the increased voltage would cause a higher current to try and flow through the filament. So when a higher current tries to flow through that filament, this tube begins to have a higher and higher resistance. And when it does so, more voltage is dropped across this ballast tube, leaving less voltage on the filament. So in effect, it keeps this voltage on the filament relatively constant, and the voltage variation and that drop occurs across this ballast tube. So if you were to look inside this tube when it's functioning, the filament is a very, very thin, almost hair-thin type of filament, and it doesn't glow like a normal vacuum tube. You might see only a portion of the filament glowing. In fact, it starts to glow at one end, and as more and more current flows through it, more of the filament actually glows. So under normal use, the whole filament is not glowing. That would actually be an indication of a problem. It shouldn't be glowing, like a normal tube does. So a rather unique tube and interesting tube, particularly when you look inside. They almost look like there's nothing in there because the filament is so small to actually see it. You can see the mica, spacers and the standoffs and pieces that hold the filament, but the actual filament is extremely small in those tubes. So again, rather unique tube, but its job is to just simply regulate the voltage on that filament. So over here we have a 12AU7. And you can see on the schematic, when you have a tube that has sort of this broken or dashed line on part of it, it means that there's more of that tube somewhere on the schematic. This is only part of it. Well, up here, of course, here's the other half. You can see it says half 12AU7. So 12AU7 has two triode sections in that tube, and they're being used as the driver, to drive the meter movement right here. So over here, the EA52 is a rectifier tube. And the reason they used a rectifier tube in the input or the sensing part of this metering circuit is because back in the day when this amplifier was built, they didn't have a diode that could function up to 500 megahertz where this amplifier can work up to. So at 500 megahertz, it would require a diode that could switch on and off very, very fast. And such a diode just wasn't available, and it could be done much easier and more reliably, more accurately with a vacuum tube type rectifier. So it's a very special rectifier tube. And in fact, you'll find this same rectifier tube used in active probes. The plate of this tube right here, and you can see the plate going up here to the RF output. In this application, it's just in a holder and it's in place in the chassis. But this tube can be used in active probes, and the tube itself has a very sharp pin, and that pin can be the probe pin or the end of the probe. So that way you have virtually no distance from this plate to your probe, in an active probe. So you will find that tube in numerous and different applications. Rather interesting looking type of tube. So in this application, again, we have the RF voltage being sensed off of the output. It is rectified in this tube, becomes a DC voltage, and that DC voltage is then used in the rest of the circuit. These resistors and the range switch is just selecting the range that the meter will read at, and that switch is on the front panel. Now looking at the top of the schematic, we can see the three tubes that make up the amplifier section, V101, 102, and 103. So those tubes are the 2C39A, could also be the 2C39B, it's an interchangeable tube. These are configured as a grounded grid amplifier, all three stages. So the RF input is applied over here, and you can see that the coupling between the stages has the variable capacitor and those coils that are mounted on those turrets that we previously looked at. On the schematic, you can see these dashed lines that go around and then come up over here. That's showing that those capacitors are ganged together. In other words, they all move in unison. And again, the coils, you can see they're ganged together with those dashed lines, and those are on those movable turrets. That provides the coupling between the stages and then the output impedance right here. So again, the flow for the RF is from the input through the three stages, out of this final coupling, and out into the front panel RF output. Now you can see on the filament, it is shown on these three tubes, and that filament has some additional filtering right here through some inductors, some capacitors, these feed-through capacitors right here. This dashed line is indicating that enclosed box that holds the amplifier section. These capacitors are feed-through caps for the filament lines you can see there and over here. Some additional filtering, resistor, and so on, just to ensure that this is a very clean AC input on those tubes. You can see it's marked as 5.8 volts AC in those three tubes. Now, tubes down here, like the 6AS7, the 6AU6, the filament is not shown right at the tube, but if you look at the schematic over here, you'll see V107, V106. That's the filament for the respective tube. A rectifier tube like this, the filament is part of the rectifier. It's the cathode as well as the filament, so of course it is shown. Again, the 12AU7, same deal. The filament is not shown right at the tube. This filament does happen to be shown over there. So now this amplifier is rated 4.5 watts of RF output over here. So of course we'll be checking to see that it can produce that RF output, but you can see that a 4.5 watt output would be considerably higher than an average signal generator would be able to produce. So a very low input from the signal generator over here can produce a substantial RF output, and it could be very handy for testing devices that needs a higher level RF output, where a normal signal generator's output would be much, much too low. The impedance on the input and output is the standard 50 ohm impedance. So the next thing to do is get the amplifier powered up, and I'll be using that isolation transformer and current limited variac. So I'll be back as soon as I get everything in position and connected. Okay, I have the amplifier connected to the current limited isolation transformer and variac, so we're ready to power up the amplifier. So if you're following along and working on one of these amplifiers, please know that you do so at your own risk. These amplifiers have high voltage throughout most of the circuitry internally, and very dangerous if you don't know what you're doing, so please read up on the dangers of working on vacuum tube circuitry and know what's involved and the precautions that you need to take to do so safely. So again, if you're working on something like this, you do so at your own risk. Okay, I'll turn on the isolation transformer, and the variac is set to produce about 50 volts at this point, and the incandescent lamp is between the variac and the amplifier. So we'll go ahead and turn on the amplifier. All right, the incandescent bulb is glowing dimly, so that's good to see. It's not excessively bright. So I do feel some airflow, so the fan is running. It's just a very slight, you can hardly hear it, but again, you can feel a little bit of airflow. It's drawing in some air. The bulb is remaining fairly dim at this point, but that's good. It doesn't look like there's any excessive current draw. I'll increase the voltage a bit more. So now, just starting to hear the fan run a bit more in there. It's about 90 volts on the isolation transformer. Now through that incandescent lamp there is some voltage drop, so it's not producing or putting the full 90 volts onto the power amplifier. Yeah, we can definitely feel some more airflow, so that fan is running. So the meter has started to rise up a little bit here, so it looks like we have some activity. Now with no input voltage, or no RF input voltage, there should be no output, of course, so that meter would rest at 0, but again, the 0 adjustment would need to be set, and right now the circuits wouldn't be, in a position, or in a condition rather, to function with just such a low voltage, so some unusual indications on the meter would be normal at this point. So you can see the meter has started to rise up a little bit, and also there's a faint glow on the power on indicator lamp, or the pilot lamp. So this meter, it's normal that it would be rising up right now because the circuits are only partially powered up, and at some point when everything's powered up correctly, this would need to be zeroed out. So right now it doesn't look like that's, it wants to do a little something, making a little bit of a wiggle in the meter. So I'll let the amplifier run for a few more minutes at this low voltage. All right, about 10 minutes has gone by, and I'm going to increase the voltage now. So the variac is set to about 120 volts, and the current limiting lamp is still in place. So the lamp is glowing, but not particularly bright, so that's a good sign. The fan speed has come up a bit more. You can possibly hear it. I don't know if the camera's picking that up, but yeah, there's definitely some more airflow back there. It's picking up some speed. So far nothing smells hot, no smoke, so all good things. Seems to be powering up okay. So what I'm going to do at this point is let the amplifier sit here for about a half an hour at this voltage level and with the incandescent lamp in place. Okay, so it's been a little over half an hour at this point, about closer to 40 minutes, and the amplifier is still just sitting here with no issues, no smoke, nothing smells hot. The incandescent lamp hasn't changed in its brilliance. The meter is sort of leveled off, it's just sitting here. Again, there's no input or output, so if everything is functioning normally with normal voltages, you would zero that meter out. So now I'll go ahead and put the full line voltage just using the isolation transformer and no current limiting lamp. So we'll see if the amplifier is able to power up with the full 120 volt input. Alright, I have the amplifier connected directly to the isolation transformer, so it'll be supplying the full AC line voltage to the amplifier. So the isolation transformer is turned on. Let's see what happens. Definitely hear some fan noise there. So the meter went up there a little bit and then came back down. And look at that, so the meter adjustment seems to be working. So again, this adjustment is to electrically zero the meter. It zeroes in all the ranges. So that looks good. So it appears that the amplifier is able to power up completely with no issues. Again, nothing smells hot, no smoke, no serious problems like that. You'll notice I also put this cover back in place up here so that the forced air cooling can continue to go over those tubes. I didn't want to test the amp with this cover off because those tubes do need to be cooled. Okay, I have the signal generator set up, and you can see right now it's set to put out 100 millivolts, and the frequency is set for 15 megahertz. 15 megahertz is comfortably within the first band on the amplifier, so it'll make a good starting point. So I'll switch on the signal generator in just a moment. Let's take a look at the amplifier now. Alright, here we are looking at the front of the amplifier, and on this side you can see the RF input. This is coming from the signal generator. On the RF output side, it goes into a T connection, and we have the 50 ohm dummy load. This is rated for 15 watts, and it's good from DC to 500 megahertz, so well within the range that we'll be testing here. And then this coax cable goes up to the oscilloscope so that we can monitor the output waveform and the output level. So we'll be watching for an indication on the RF voltmeter here, and we'll want to see if this corresponds to what the oscilloscope is showing us. So I'll go ahead and switch on the signal generator. So the signal generator is now turned on, and we can see that there is an indication here, so that's good to see. And I'm looking at the oscilloscope and I do see a waveform, so that looks good as well. I'll zoom the camera in on the oscilloscope in just a moment. So the first thing, I set this at 15 megahertz over here, megacycles in the old format there, but megahertz. And what we want to see is if this peaks up or down. So that's, yeah, it does peak considerably higher there. So the oscilloscope is looking very good as well, has a nice clean looking waveform. So we definitely have some amplification going on, because right now we have 100 millivolts going in, and on the output it looks like just shy of 3 volts RMS. So the oscilloscope is saying 2.9 volts RMS, and on here this is on the 3 volt scale, so from 0 to 3 on the bottom scale, and this is showing just a little over 2, so reading just a little bit lower than what the scope is showing, but we do have some indications, so that's a good thing. Switch that to the 10 volt range. and it does show about the same. It's still reading 2 volts on the 0 to 10 scale, so the 3 and the 10 match, and that's pretty low. Really can't make much out. 10, 2 right there. So it's, you would normally use the 0 to 30 scale on such a low signal, but it's reading a little bit under 2. Let me zoom in on the oscilloscope. You can see the signal that's coming out of the amplifier. Alright, here's a view of the oscilloscope, and you can see we have about a 3 volt signal. It was about 2.9, now it's showing about 3 volts. So about a 3 volt RMS signal, and that's with 100 millivolts going into the amplifier, so definitely some amplification going on. Now, with a 3 volt signal coming out of the amplifier into that 50 ohm load, that's 180 milliwatts. So this amplifier is rated to go to about 4.5 watts. So let's increase the input voltage and see if we can get a little bit higher output level. Alright, now I've increased the signal generator to 270 millivolts. And with the 270 millivolts going into the amplifier, we can see a 7 volt output. And with 7 volts coming out of the amplifier, that's equivalent to a 1 watt load into the 50 ohm dummy load. The amplifier is indicating, looks like on the 0 to 10 volt scale, about 5 volts. So that meter looks like it's reading, a little bit low still. We'll have to look at the calibration on that meter, but definitely giving us some indication and certainly giving some amplification on that signal. As you can see on the oscilloscope, it's showing 7 volts, about 7.1. So now, to obtain a 4 watt output on the amplifier, that would be 14.14 volts. So let's see if the amp can do it. Okay, I have the signal generator increased to 580 millivolts, and you can see on the oscilloscope it's indicating about 14.1 volts RMS. So that's giving us our 4 watts into the 50 ohm dummy load. So the amplifier is functioning very well, and it's looking very good so far. Alright, so we know that amplifier is able to power up and is working well enough to pass an RF signal and is able to amplify that signal. And we know there's no serious problems such as a burned out transformer or something like that. All the tubes are functioning, the RF stages are able to pass the signal. The front panel meter and switches are all working, so it gives us an overall feel for the condition of the amplifier. So now going forward, we'll take a look at some specific components that need repair or replacement, and I'll share that with you. The next thing that I did was to clean the chassis up and also the front panel. So there was the typical grit and grime that had built up, and that needed to be cleaned out. So you can see it turned out really nice down in here. Everything's been cleaned up. I removed all the tubes, removed the fan off of the lower part of the chassis, removed the meter off of the front panel, the front panel handles, all the knobs, and just took some time and cleaned everything up. Used some compressed air, blew the dust and lint out of some of the corners, hard to reach areas. Use caution if you have compressed air. You don't want to use a strong compressed air around delicate components, of course. For cleaning the chassis, I find these blue shop towels work really well. These industrial towels, they hold together, they're really strong, particularly when they're wet with the cleaner, and they last a long time. One towel will do quite a bit of cleaning, so they're in no way a sponsor. It's just a product that I find works well. And I just dampen the towel with Windex and wipe the chassis down, wipe the front panel down. And the front panel was looking a little bit dull, so to kind of revitalize that, bring some new life to the front panel, also use it on the knobs. This product called Glaze It works really well. Again, in no way a sponsor, just a product that I find works well and that I've been happy with. I've also used Glaze It on Bakelite, and it works really well. It really rejuvenates and revitalizes the Bakelite. Something I like about Glaze It is that it does not leave an oily residue. So you can use it on front panels, control knobs, things like that. Bare metal surfaces, even like these handles I wipe down on the front panel. And it just really revitalizes and brings a new life to the front panel. So it turned out really nice. It looks really good, so I'm very happy with that. Alright, you'll notice that a vacuum tube is missing right here. That tube has been removed, and I'll explain what's going on with this tube. So earlier in the video, you'll recall this makeshift clamp that someone had put in here. It was just this wire that had been wrapped around the holder for the tube. And I commented on that. It didn't look too secure and it would need to be, replaced or taken care of. So of course I don't have the original clamp, and I couldn't find a clamp that was ready-made that would work. So I went ahead and made my own clamp right here. So it turned out really nice and should do the job. And a very small screw right here and nut like this. You can see there's the hardware to hold everything together. So when that wire was untwisted and the tube becomes immediately loose in this holder, and so I went ahead and just removed the tube completely, and I thought, well, that'll give access under the tube, and I can examine down in here while the tube is out, take a closer look at some of the components. Clearly it had been worked on. Someone either replaced that tube or was testing something. It's hard to say what was going on, but it's, again, when you see an issue like that where it's not original, you want to examine components around and make sure that everything is in good order. And in this case, there was another problem. So right here, you'll see this contact, very thin, almost like a foil type material, this metallic contact, which is supposed to be connecting to the plate of the vacuum tube. So the plate of the vacuum tube is this outer ring right here, and this clamp goes around that ring. And the purpose of that clamp is to hold or squeeze this contact finger right here. And that's what makes contact to the plate circuit. This is the variable capacitor, one of the variable capacitors right here that it's attached to. So that was just touching. It was not actually under that clamp. So that could easily become intermittent, and then the whole amplifier would fail. And again, not real obvious when the tube was installed, but as soon as the tube became loose in the holder and I lifted it out, that was not even attached underneath. So the next step will be to get the tube reinstalled and to repair or replace this material that's in here, and make sure that that makes a good connection to the clamp like it's supposed to. Also, in the back of the vacuum tube, you can see here's the tube again, and on the back side, this clip right here goes to right here on the vacuum tube. It's the cathode. This is a little capacitor right here, and this tab of the capacitor attaches to this coax cable right here. And the filament is this inductor, and then this inductor right here, which is attached to this clip, and this clip goes on this part of the tube right here. Those filament leads attached to this feed-through capacitor here and here, so these 2 points. So I'll reposition the camera and I will show you another problem that I found regarding these variable capacitors. Okay, here we are looking at the other side of the amplifier, and you can see the 6 tuning capacitors here and here, here in the middle and down there. These are the adjustments for those capacitors. So you'll recall earlier in the video I commented that this was very stiff and difficult to turn, the adjustment. Well, you can see now that's been taken care of. This rotates very easily now. It was making some grinding sounds before and just, really difficult to make the adjustment. It didn't rotate correctly at all. So the problem really was in these bearings and numerous pivot points around in here. It just needed to be cleaned and oiled and made it function much easier. There's also a vernier control, and the bearing on that vernier control was really stiff and dry. So that's all been taken care of, and it's functioning really well now. However, once that was taken care of, the lower capacitor section I noticed was not moving correctly. So what was happening is this bottom section was stuck in like so. So now you can see this top section would rotate like this, but the bottom section right here was not moving out the way it was supposed to. It was stuck in. So that was affecting the tuning on the amplifier. basically making it very limited on the usable frequencies that it would function at. So the problem was not so much in the pivot down here on this lower section, but in the pistons in the capacitors and on all three of them. So some contact cleaner and just working it back and forth really freed that up. But it took a little bit of doing because it was very stiff and had probably been years since it had actually moved in its full range. So that's taken care of now, and it's working really well. And you can see it tracks or moves against those cams as you rotate those back and forth. The vernier control is working really well too. It's very smooth when you turn that. Gives a very fine adjustment range. So the mechanical part of this amplifier is working well. And we'll take a look underneath on the electronics, and I'll show you some other issues and what needs to be repaired next. Okay, here we are looking at the bottom of the amplifier, and you can see this is below the vacuum tubes. So these capacitors, I've already commented, need to be replaced, and I'll be doing that next. So while cleaning the chassis and just inspecting components in general, I noticed that this resistor has a crack on the side. It's kind of swollen, so it's probably been overheated at some point. So it needs to be replaced, and this resistor and these two each are 2 watt, 330 milliohm or 0.33 ohm resistors. So there's one resistor per RF power tube, and they're in the filament circuit. They're in series with the filament. So the power transformer has 3 dedicated windings for the filaments, one winding per RF power tube. So I'll go ahead and change all 3 of these resistors. They're certainly easy to do, so we'll get that taken care of. Okay, right here you can see there's a resistor that comes over to a solder connection on a feed-through capacitor, and this solder connection was broken. So I've already fixed that, just freshened that up with a little bit of new solder. But that connection was broken. It was just touching. There was a little bit of a J-hook on the end of the resistor lead, and it was just resting against that terminal. So making enough connection that the meter was, making a reading, but it certainly could have been intermittent at any moment. Now, in this little box or housing right here is where that vacuum tube rectifier is located that takes the reading off of the RF output signal. So when you're cleaning the chassis and just inspecting components in general, make sure to look at the small details. Components that are severely overheated or maybe a leaking capacitor might be really obvious, but a small crack in a resistor might not be so obvious. So take your time and really just work through methodically on the circuit and take a close look at the components. And when you're in here, just gently press on components like so. Look for any solder connections that are loose or broken, and take care of those issues as you find them. I didn't notice this solder was broken until I actually pressed on this resistor, and then I saw this move over here. Okay, here we are looking down on the top of the power amplifier. You can see this vacuum tube has been reinstalled in the output stage, and here's that clamp that I fabricated, so it's in place and keeping this vacuum tube secure in the holder. You can see I modeled it after this original clamp over here, so it's the same design, and it's working very well. So now let me reposition the amplifier, and we can take a look at the bottom of the chassis and the components that were replaced. Okay, here we are looking at the bottom of the chassis again, and you can see the various components that I've replaced. So we have the 4 capacitors here, 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 and this one in the clamp right here. And then the 3 resistors here, here, and right here. So you can see there's a noticeable difference in size on the capacitors on the old versus the new. So this capacitor right here and the old capacitor, you can see there's a considerable difference in size. Now this old capacitor was rated 40 microfarad at 500 volts, and the new capacitor is 47 microfarad at 500 volts. So when replacing capacitors, it's perfectly fine to increase the capacitance if necessary. You could also lower the capacitance slightly. Sometimes on these old components like this capacitor, a 40 microfarad 500 volt was just not a common value, but a 47 microfarad is a common value now, so perfectly fine to increase that capacitance slightly. But with capacitors, you never want to replace it with a lower voltage rating, so you always need to go equal or higher in the voltage rating. Of course, within reason. I mean, you wouldn't go in here and put, 1,000-volt capacitor or something like that. But again, within reason, increasing it slightly is perfectly fine. You can see this capacitor, the Goodall wax capacitor, 1 microfarad, 200 volts, and the replacement right here. So again, a considerable difference in size. You can see the 0.1 microfarad capacitor, the old one right here, and then the new capacitor right here. The new one is rated 630 volts. The old one was a 500 volt. And the 8 microfarad capacitor right here is rated 450 volts. The replacement is identical, 8 microfarad, 450 volts. Now this capacitor over here, I mounted in a new clamp that fit the new diameter, but I kept the same mounting location and the wires running to it the same design as the original had. This old 8 microfarad capacitor had the clamp that was holding it in place, and it was originally on this threaded stud. The new capacitor, I opted not to use a clamp. It just doesn't weigh enough to need any additional support. It just is perfectly fine like that. This old wax capacitor had a clamp that was holding it in place, but again, this new capacitor is so lightweight it just doesn't need to be supported with any additional help. This capacitor never had a clamp over here. So when replacing components, it's okay to shift components around, move things just a little bit. That's perfectly fine. Just be aware of the circuitry that's around the capacitor. So for example, this capacitor crosses these two filament lines, so you would not want to position this in parallel with those filament lines. This 8 microfarad capacitor was starting to leak a little bit. I don't know if you can see on the camera very well, but there's some corrosion that's forming down in there, and it's certainly past its due date at this point. This was the resistor that had split, and it's a little bit swollen as well. You might be able to see in the camera there. I don't know if it's going to pick up the little crack that's in the side, but turn it right in there. Get this centered up there. I think you can see it, but there's a split right in the side. So I should also mention, when replacing resistors, you always want to keep the resistance value as close as possible to the original resistor. Sometimes you'll come across old resistors that just don't have a modern direct replacement for their value, but something that's close is perfectly fine. Generally won't have any issues with the circuitry. But the watt rating should always be equal or higher. And with the carbon composition resistors, oftentimes an old 2-watt carbon composition resistor could be replaced with, say, a 3-watt resistor, and the modern 3-watt would be equal or maybe even a little smaller. So it is not a problem to replace, with a higher watt rating, as long as it fits in the circuit. Of course, you wouldn't be replacing a resistor like this with, say, a 10-watt resistor. It wouldn't be practical, and it just wouldn't fit. So now that all the repairs are done on the amplifier, let me reposition it and connect it to the signal generator and a dummy load, and also to the oscilloscope, and let's power it up and see if it functions. Okay, I have the power amplifier in position, and it's connected to the isolation transformer. So the first thing we need to do is check the B+ voltage. Several of the capacitors that were replaced are in the B+ circuit, so that could easily affect the voltage, and we just need to make sure that the voltage adjustment is set correctly. So R107 right here is that adjustment. Now the digital multimeter is connected to the plate of this vacuum tube, and that plate of the tube is connected directly to the B+. So it makes a convenient test point, and then the negative lead of the meter is just connected to the chassis, which is ground. So the isolation transformer is turned on, and I'll go ahead and turn on the amplifier now. So watching the multimeter, you want to see that voltage come up. It should be several hundred volts. It is rising up. So the service manual calls for 320 volts for the B+, the regulated B+ voltage. The unregulated voltage going into the 6AS7 tube is over 400 volts. So I'll let the amplifier warm up for a little bit. So the amplifier's been powered up for several minutes now, and the voltage is stabilized at 312.8. So again, 320 volts is what the service manual calls for, so we'll make that adjustment now. Just a slight adjustment on R107. Sets exactly on 320, so that looks very good. So I'll let the amplifier run for a few more minutes and make sure that that voltage, continues to regulate correctly and hold at 320 volts. And then we'll continue on with testing the amplifier. Okay, the power amplifier is turned on, and on this side the RF input is connected to the signal generator, but the signal generator is not putting out a signal right now, it's turned off. And the RF output over here is connected to a 50 ohm dummy load and to the oscilloscope. Now there's an adjustment, you can't see it on the camera, but down in the chassis over here, it's R113, it's diode compensation. And the purpose of that is so that when you change the range from 3, 10, and 30 right here on this selector switch, that the meter stays at 0. Now as you recall, this adjustment is an electrical 0. You can see how the meter moves, while I'm turning that adjustment. So when I look straight on at the meter, right there, that's 0. Now I know on the camera it may not look like that needle is resting right on 0, but when you look straight in, a straight view on the front, it is at 0. So I went ahead and made the adjustment on that diode compensation so that this is now correct. When it's on 3, 10, and 30, this does not move off of 0. It remains stationary. So I'll put that back on the 10 range. Okay, here we are at the RF signal generator, and you can see the output is set for 50 millivolts at 100 megahertz. So we'll use that as our initial starting point. So I'll switch on the signal generator. And we do have an indication on the amplifier, so let's take a look at that. Okay, here we are back at the power amplifier, and you can see there's a indication on the RF level meter right here. So let's start by peaking this up a little bit if it needs that. Yes, it does. So up here. So right about there. So that's looking like just about 3.5 volts. And on the oscilloscope, it's indicating about 3.4, so not bad. Yeah, it's not bad at all. Now there is an adjustment for the meter. It's R125, it's the meter sensitivity. It's an adjustment down here in the chassis, so I can adjust that if necessary. But it seems very close at this point. So let me increase the signal generator output here. You can see that goes up nicely. Okay, I increased the output level on the RF signal generator while watching this RF level meter on the front panel and also the oscilloscope, and I stopped when this got to 10 volts. The oscilloscope is also indicating 10 volts, and the signal generator is at 188 millivolts. So we definitely have some amplification occurring, and the meter is looking very good. The tuning over here is working very well. Here's a view of the oscilloscope. Okay, here's the 50 ohm dummy load, and you can see the coax cable that's coming from the output of the signal generator power amplifier. This is just a T connection right here, and then this goes into the oscilloscope. So here's a view of the oscilloscope. Pardon the flickering on the screen, that's just the CRT refresh rate, and it kind of conflicts with the shutter in the camera. Gives that rolling effect. It does not look like that when I'm viewing it, but it does on the camera. So you can see the output looks very good, and you can see the frequency indication at 100 megahertz and the output at 10 volts. Okay, I now have the RF signal generator set to 315 millivolts output, still at 100 megahertz. And you can see on the RF level meter right here, it's indicating 15 volts. The oscilloscope is also showing 15 volts. So 15 volts into the 50 ohm dummy load gives us 4.5 watts of power. So this amplifier is rated 4.5 watts, and it's able to meet that specification. So it's looking very good at this point. Okay, here's a view of the oscilloscope, and you can see the 15 volt signal at 100 megahertz. So 15 volts into the 50 ohm dummy load is giving us the 4.5 watts of power coming from the amplifier. Okay, I now have the power amplifier set to a different frequency range on the band switch. It's in the 18.5 to 35 megahertz range, and the RF signal generator is changed over to 20 megahertz and a 183 millivolt output. That 183 millivolt output is giving us a 15 volt output on the RF amplifier. So that 15 volts into the 50 ohm dummy load is the 4.5 watts. So the amplifier is looking very good. You can see if I change the tuning on the amplifier, that signal attenuates, and it's peaked up about there. 15.1. So again, looking very good. Okay, here we are looking down on the top of the power amplifier. So the amplifier is still powered up and running, but there's no RF input being applied to it. So as you recall, the amplifier has 6 tuning ranges or band switch positions that switch on the front panel, and it controls the movable turrets in here, and the 3 amplifier sections that have those tuned RF coils on them. So as I work my way through the entire frequency range, I found the amplifier is functioning very well, so no further issues. Now, you can see down here on the lower part of the chassis, there's R125, the meter sensitivity adjustment, that variable resistor down there. And that needed some slight adjustment to compensate from the lowest frequency extreme, 10 megahertz, up to 500 megahertz. If you set it so that it's spot on, say at 15 megahertz or somewhere in the lower frequency ranges, by the time you hit 500 megahertz, there was a little more error than I wanted to see. So really just a balance between those two extremes, and the reading on the meter is very acceptable at this point. So again, no further issues. So the final thing that we need to do is take one last reading on the B+ voltage just to make sure that it remains okay. Again, it's that regulated B+, and you can see down here R107, the voltage adjustment. We can adjust that if needed. So that convenient test point is the plate of the output tube under this cover. So during all of the testing, particularly when the amplifier was under load, I had this cover in position with just the one screw holding it in, securely in place. If you're operating one of these amplifiers, you can run it with the cover off for short periods of time, particularly if there's no load on the amplifier. But if those output 3 RF tubes, and particularly the output tube, is operating under load, then it does need to have the forced air cooling to keep those tubes operating in a safe region. So I'll take this cover off now. Now again, the amplifier is operating, and there's very high voltage under this cover. So if you're working on one of these amplifiers, you need to use extreme caution. So I'll connect the ground lead to the chassis over here, like so. We'll take the reading across here, keep this up above the tubes, like so. So we can see it's 319.7. So that's looking very good. So that hasn't drifted or changed in its reading, by any considerable amount. The service manual gives an allowable range. It can shift or change by about 5 volts. And again, that's that regulated B+ off of this 6AS7 tube right here. It's controlling that. Now this tube over here In this section, this is the RF input, so the flow of the RF is from this tube through like that. And this tube, its plate is at a lower voltage. There's a resistor in series with that plate. So you can take a reading on here, but it's not the complete or full B+ voltage. You can see it's 214.2. So if you do use these tubes as a test point for that B+, again, you need to use this tube back here. 319.8, so looking very good. So now I'll power down the amplifier and I'll reinstall that top cover, the aluminum cover here. The top and bottom cover on the amplifier section has this wire mesh that is installed underneath the covers. It's part of the shielding that just is from the factory that way, and it is installed first and then the cover goes over it. Again, the top and bottom covers both have this wire mesh, so I'll put that in position and reattach the cover, and then we'll put the amplifier back in its outside case or housing and finish up the project. Okay, you can see the bottom cover has been reinstalled and is securely in place. And the cover over the amplifier section is also reinstalled with the 8 screws that hold it in place. So the final thing I need to do is reinstall the top cover and also reattach the air intake filter. So I'll do that next. So the repair and restoration on this Boonton Radio Company 230A signal generator power amplifier is now complete. If you enjoyed this video, don't forget to give a thumbs up. If you haven't subscribed to this channel, now would be a good time to do so. I'll be featuring more projects like this, both vacuum tube and solid state, repairs, restorations, and how-to videos. So until next time, goodbye.